Good afternoon, everybody. My name is Shaun Fitzgerald. I'm with the Centre for Climate Repair, based at the University of Cambridge and actually headquartered here in the Department of Applied Mathematics, which is wonderful. I'm joined today by Jacob Pantling, a PhD student in the topic of ice thickening, and Andrea Ceccolini, who is from an organisation called Real Ice. And we have had the really lovely opportunity to get to know Real Ice over the last year, and it was serendipitous. Andrea reached out to us and really sort of struck a chord in terms of just bringing complementary skills and interests in trying to answer the question of, can we grow more sea ice in the Arctic? So I thought I would just start by just giving an overview of what's really going on and why this question we think is interesting and has merit to be explored. There are different ways that you can assess what's happening in the Arctic and the changes. You can look at just the ice cover, and the ice cover matters significantly because the ice cover of sea ice, there's a very big difference between when the ocean is covered with ice and when it's not, when the sun is shining. And in the Arctic, although the sun might not be as directly incident, therefore the angle isn't quite the same as over the equator, in the Arctic summer it shines for rather longer than it does on the equator, and it's the cumulative effect that matters. So the figure on the left, known as the death spiral, is really looking at the aerial extent. This is like the radius on the starting from the middle, actually, as the years have unfolded. So this is changing every year as we squeeze more years in. And then the lines themselves show actually what's happening on a month-by-month basis. And it's really, when we talk about the Arctic ice minimum, we're looking really at what happens around September. The graph on the right-hand side is from a more recent publication by Shaun et al. In 2024, and looking at what they deem to be in terms of probabilities for what they call an ice-free Arctic. And by ice-free Arctic, what we mean is that at one particular point in the year, there being less than 1 million square kilometers. And the modeling that's been done here is looking at different shared socioeconomic pathways. These are used in the IPCC reports. And the essence being that it's looking pretty horrible. It's looking likely, very likely, that there will be, quote, no Arctic sea ice by, let's say, mid-century. Certainly we're going to be by the end of the century, things are looking very, very ugly indeed. So that has massive implications in terms of, therefore, the overall radiation balance for the Earth, and of course, all of the ecosystems and the people and the livelihoods of people who live in the Arctic as well. So it's a local, regional impact, as well as an impact on the world overall. And one of the ideas that's been proposed, it was about 2016 that I first came into the publication, that I first heard about this, was, what can we do to not just think about the reflection? There are different ways of climate engineering that have been proposed, looking at playing the radiation game with things like marine cloud brightening or stratospheric aerosol injection. What can we do to try and get more sea ice to form in the Arctic winter? So it's actually ultimately, instead of playing the reflection game, it's more like playing the radiation game. Because if you're going to create more ice in the Arctic winter, that means that you're dealing with the latent heat of solidification and therefore getting rid of that heat and radiating it out into the Arctic winter, into the dark sky. And there are two basic concepts. So as ice is less dense than water, it floats. When the ice starts to form, it's on the top. And therefore, what happens is that the new ice that's forming does so as a result of the solidification of some of the water on the underside of the ice. And then what happens to that latent heat of solidification? It needs to be conducted through the ice. And then once it's on the surface, it can then get radiated out to space. But the ice is an insulator. Therefore, sort of as a thought experiment, if you think everything else being equal, as the ice thickens, you have a bigger insulator, and therefore the rate at which more ice can be basically created decreases over the winter, decreases as the ice thickens. So one idea is that to try and overcome that challenge is to pump seawater on top of the sea ice. So change the way that the ice forms by actually having freezing from above and getting that water in contact with the directly with the Arctic sky and with the Arctic air. So that's concept number one. Concept number two is a slight twist on that, is that instead of doing all of the freezing by the addition of pumping, the action of pumping, recognizing that certainly in the early part of the winter, in addition to sea ice, you then have snow that forms on top of that ice. And if you think ice is a good insulator, well, snow is even better. So the twist is that if you were to pump some seawater on top of the sea ice and just fill the voids that are previously occupied with air, hence the snow, if you fill those voids with salt water, with seawater, and then allow that to solidify, you've consolidated what was a light fluffy snow into a more solid ice matrix. And the overall result is that the total conductivity of the ice is greater than the previous ice-snow matrix, and therefore you will enable the natural rate of freezing from underside to actually be faster. So that's a twist. And the initial analysis that's been done suggests that the amount of energy, pumping energy, that you need in order to create a certain increase in ice extent through the snow flooding is less than the amount of additional energy that you would need by pumping on top of the sea ice itself. So you might think that's a good idea. We don't know whether it's a really great idea. We're going to go and explore that. But secondly, energy isn't the only metric that we need to worry about, because you also then need to think about, well, if you've pumped and you've now flooded the snow, you have a logistics challenge with just moving this thing around. And that therefore becomes there are different challenges. There's not that one is necessarily better than the other. They have different characteristics. And the last thing that I wanted to sort of just leave you with before I hand the baton over to my colleagues is that certainly when you pump seawater on top of sea ice, we have to recognize that that's a very different process than the way that sea ice forms naturally. When sea ice forms naturally and you've got crystallization, so crystals of H2O forming, so the solid form of water on the underside of the ice, the brine that's left is pretty dense and therefore has a natural tendency to fall. Whereas now we're bringing the salt water on top of the ice, and there are some outstanding, I don't mean brilliant, but I mean outstanding questions, ones we need to resolve, are the fact, what happens to that brine and how much of it gets retained, trapped by the ice assembly, how much of it self-burrows and therefore is expelled, and therefore you're left with relatively fresh ice. All of these questions are still to be answered, which is why we're not here today saying this is the answer, but we are here saying we think these are important questions, and we've started doing some research, and we'd like to share that with you, but leave you with hopefully still lots of unanswered questions. But anyway, over to Jacob.
Okay, so I'm going to take us right back now to the modelling which we started with, which is just what happens when water flows over ice. And you might think that's a relatively simple problem. It's been researched well. Well, it turns out it's not. And so that's what I've started with, just fresh water flowing over pure ice and what happens. And as Herbert first identified, who's in the audience, if you put warm water or water of any temperature on cold ice and it's flowing over the surface, the first thing that happens is freezing. And the reason for that is you get a sharp, very sharp temperature gradient in the ice at the surface, because the interface between water and ice must be at the freezing temperature. If it was warmer than that, then ice would have melted. Or if it's colder than that, then water would have frozen instantaneously when they first came into contact, which is non-visible. So the interface is at the freezing temperature, and there's an infinite temperature gradient in the ice, but you've got a constant supply of water temperature because that's flowing over the surface. And so what happens is you get a very high rate of conduction tending to infinity in the ice, and you get freezing initially. But then what happens as the temperature gradient weakens, as heat is conducted into the ice? Well, you still get freezing, it's still greater than the heat supplied by the water, but at some point they balance and you get a constant ice thickness, and then quickly the water advection to the ice exceeds what the ice can conduct, and you get melting of the ice that you formed, and then melting of the original ice that was there, which obviously is not what we want. But that's what happens if the water is warm, which is what we're first considering. So we can then do some modeling of how the ice progresses. And so we've got time here on the x-axis and distance from where you're injecting the water on the y-axis. So water flowing down a channel in one dimension. And the plot here, the colors are ice accumulation in blue and melting in red, which is bad. And we can see that over time, we get a region of ice where there's a little bit of melting at the inlet, but for the vast majority, further, you get freezing and accumulation of ice. And that's really what we're interested in. So we've coupled that with lab experiments, obviously. So here is Trinity College meat freezer. Not the best place for me to do my experiments, unfortunately, but they very kindly allowed us to do. This is one day where I couldn't go in because it was full of food, which is fair enough. But here's my setup on the right-hand side. So this is the channel that water's flowing down. We've got water in a bucket here with its temperature being measured, and then it's being pumped onto the surface and flowing in a thin film over the surface there. And so we've got some results for 0.5 degree and 0.8 degree water flowing over the surface. So close to the freezing temperature, but slightly above it. As you can see, we get some melting and we get some freezing further away, which is what we predicted. And so the green plot here is the one that was on the color map earlier. So that's for a viscous flow with a thermal boundary layer. We've also got an inviscid flow with no thermal boundary layer. So that's a bulk temperature that's decreasing as we're going along the channel. And we've also got an inviscid flow with a thermal boundary layer. And as you can see, the best model, the one that matches more closely to the data, is the viscous thermal boundary layer model. And so what happens when we go slightly warmer? And this is at 2 degrees. As you can see, it doesn't match any of the plots, any of the prediction. And there's a couple of potential reasons for this. So this big area here, where there's a big decrease in the ice, there's 2 reasons why that causes issues with our models. So the first one is we've assumed that the water is flowing over a thin film over the whole length of the channel. But in reality, in that location where there's a big hole, the water's pooled and it's just sitting there. And the second reason is that we've simplified our calculations by taking heat transfer to be occurring at the initial location of the water ice interface. So as the ice is melted, that interface has moved, and it's obviously moved a lot more with the warmer water. And so that's another reason why our models might not be matching as well to the data at the warmer temperatures. So then we've moved on to 2-dimensional flow. We're considering the second end member of, are we, in the real case, is it going to flow as a channel? Is it going to flow radially? It's going to be a combination of the two in the real case, but now we're looking at the radial flow. And so as the water flows outwards, we're considering, again, inviscid and viscous flows. And as the water now flows out, there's the heat transfer by advection from the water is decreasing more rapidly because we've got a smaller volume of water per unit area. So the temperature of the water is decreasing more rapidly, and we get lower heat transfer from the water. So we expect more ice to grow more quickly. And if we have the same model again, then that's what we see. We see a much smaller region of melting because the boundary layer is much thicker between the water and the ice, and therefore we get a much lower rate of advection. And this radius is much smaller than the previous one, and even so, we've got a very small region of melting when we're in the radial case, which is encouraging. And so we've also done experiments for the 2D case. First, I moved to a chest freezer in the engineering department, much easier, and they didn't have food in, but more difficult to control in terms of temperature and things. So now we're in the cold room here in Dampt, which is very nice controlled temperature. I'm the only person using it currently, and it's the right place to do experiments compared to a Trinity meat freezer in their kitchens or a chest freezer. And so we've got some more results for 2 temperatures of water for the radial flow. And as you can see, again, we've got the same 3 colors. Of the blue line is the inviscid flow with no thermal boundary layer, and that doesn't really match to the shape of the data very nicely. Then we've got the yellow is the inviscid flow now with a thermal boundary layer, and that's just, it's sitting well below where the data is. And then finally, the green, the viscous thermal boundary layer in the, is matching quite nicely to our data compared to the other two. And that's encouraging because that's what we also saw in the first case. So moving on to my next series of experiments, I'm going to look at now what happens when we compare flooding of snow to pouring water on top of bare ice in the lab. So I'm going to have four boxes, which are all the same. And initially, I'm going to let a certain amount of ice freeze in all of them. So we're going to start off with the same, the left-hand side of each is the same, and we're going to have a certain depth of ice. And then one of them we're going to leave to grow naturally. That's the far left. Another one we're going to add water on top. So that's the freezing from above idea. And so we're going to add the water, that will freeze, but we'll get less freezing on the bottom because we've obviously increased the insulation by adding the water on top. So yes, you get more freezing, but you've reduced the rate of natural freezing. And then we're going to compare with snow. We add snow on top and then leave it. We expect there to be less growth than for the case of bare ice because the snow is a good insulator. And then we're going to flood the snow and compare that to the snow-covered ice and the other two and how that changes. So we expect it to grow more rapidly than the ice that was covered in snow, but we don't know how that might compare to the initial bare ice or to the ice that we added water onto, but where there was no snow. And so that's going to be my next series of experiments, and I'm going to use saltwater flat rather than fresh water to try and gain a better understanding of some of the effects of using salt water. So longer term planning, I'm going to look at trying to model the whole Arctic, or at least a larger area of the Arctic, to get an idea of the large scale dependencies on what happens there. Then I'm also going to do some more analysis of how many pumps will we need, what will the costs be, how difficult is this going to be from an economical and an engineering, the actual pumps and everything perspective, feeding the lab experiments into more field work, and also analysis of the field work that we've already done, which leads me to hand on to Andrea, who kindly invited me to join in January.
Thank you, Jacob. Yeah, talking about January, and well, first of all, Realize is a UK startup. We've been operating for 2 years, and we've gone to 2 field trips, one in Alaska at the beginning of 2023, and one in Canada, Nunavut, Cambridge Bay, last January. Jacob was with us. Maybe a good way to break between the 2 presentations is to show you a short video of what we did this year. Okay, so let's go back to the presentation. Never works. Why? There we go. There we go. I'm back. Okay, so as Shaun said and Jacob mentioned, what we wanted to try in this trip was to try the snow flooding method, so pumping a lot of water on the existing snow and see how the flooding gets to freezing, and then hopefully later see some additional growth or extended growth from the bottom. And this is the method that we're testing at the moment, where obviously we see what is most effective, also depending on the local conditions when we do the re-icing. So the other most important thing we were trying to test in this trip was how to do the pumping with zero emission. So we brought hydrogen with us and a fuel cell and an electric pump. So effectively, we were generating power on the field through the hydrogen, and there was no fossil fuel involved, at least in that. Clearly, going forward, this would be green hydrogen produced from renewable energy. So that's the idea of how we can scale and maintain the technology zero emission. We were doing re-icing on the same area every day, pumping water for a few hours, and we covered roughly 4,000 square meters and created about 1,000 tons of new ice. Still, a small experiment, but I think it was interesting to see how things developed, how they evolved. We initially flooded about 20-25 centimeters of snow, and we had some new snow brought by the wind on every day, so we could see how the water would move across the field every day, faster or slower based on the available snow. And then we tried to also pump on bare ice in a different area, again, to see how the water spread. We witnessed some movement of salinity. So obviously we were pumping seawater, salty water. Roughly the expectation was around 25 parts per thousand. And we saw that once we mixed it with fresh water, with the snow, then it went to a combination of 12 to 23 on the stack of the new ice that we created within a week, effectively. So we saw the migration of brine from the top to the bottom of the new ice, but we didn't see any of that going into the old ice. Possible explanation is that the old ice was still at a much lower temperature during that period, and so wouldn't allow the salt to migrate in that short period of time. And the expectation, we'll see from the lab tests whether over time that opens up a little bit and that brine managed to get into the ocean. Another important part of our trip was how do we actually get to do these projects in a way that is acceptable, lawful, and where we get the support and the help and the involvement of the local community. So we wanted to test, even though this was a small experiment, imagine a football size, we wanted to get through the full permissioning process. So this was roughly 5-6 months of work. So you see Nunavut level, so regional level, planning commission, the charts itself, so the polar station that hosted us during the test in Cambridge Bay, an impact review board from Nunavut, a research institute, finally to get to what is called the Hunters and Trappers Organization, based in Cambridge Bay, in this small hamlet, which again gave us a positive feedback and started a public consultation. So we had a 2-week period where everybody in the village was able to give feedback on this possible project. So they got our application, what we intended to do, where, and they saw that there was no, let's say, negative impact. So we were allowed to do our intervention. Again, it's small scale, but it would be the same process if we went with a larger scale at state level in Nunavut. So we understand a little bit more about the engagement with these institutions. And I have to say, once we were there, we also received very good feedback from all these people, the people we spoke with, including the local Inuit community. So I'm now going to start to say how we actually plan to do it in the larger scale. And this gets into the future sort of engineering. So one thing that we've learned from these last couple of trips is that trying to operate on top of the ice in very harsh conditions, it's not only painful for people, but it actually puts, if you want, all the engineering to very, very tough test. So the combination of cold, water, and salt really can destroy everything in minutes, literally. So everything freezes, it's tough to restart equipment. We heard from a recent, also another similar experiment just happened, that even diesel pumps, which you would think might be a little bit sort of easier to operate in the cold, were completely destroyed after like half an hour, 40 minutes of being left in the water. So it's tough to operate when you have -50 wind and all sorts of precipitation. So our idea is we want to operate from under the sea ice. If you think it's easier to move, so you can move in 3 dimensions with low energy. On top of the ice, you have pressure ridges, uneven surfaces, the ice breaks. Under the ice, you don't have any of that. You can move, avoid obstacles. And you are at a controlled temperature, roughly the -1.5, -2, depending on the salinity. So once you are in a sealed enclosure of an automated underwater vehicle, in principle, well, in principle, people do it already, your electronics and an electric pump or a hydrogen cylinder fuel cell will be able to operate without problems. An additional complexity you have is that you need to make the hole in the ice from under the ice as opposed to do it from the top. And you need to do it by limiting, if you want, the mechanical stress, because otherwise the drone wouldn't be stable. So the idea is that we have a thermal ice coring device. When we do the re-icing, if the ice is already a meter at the beginning of the winter, you don't need to intervene. The ice will grow thick enough to survive, even the following summer. That's what we see in principle. So we'll always be between maybe 30 and 60 centimeters. So we make a hole with a thermal device. We throw out the ice that is in the middle. We start to pump. We pump for hours or a day in a row. We go back to refuel and we do the next area, etc. So this is also, so this would be a modular, we see a scalable solution where the energy is provided by hubs that control many of these devices. So this is a way, by the way, how a mission would work in terms of approaching and managing. So a single hub would control many devices, would provide the energy, would see these devices go out, re-ice, come back, refuel, and so forth, until an area is fully covered, and then you can move to an adjacent area to continue the coverage. So this is our current, so if you want, engineering idea. Of course, we tested on top of the ice, and we tested the individual components with power station, with hydrogen, fuel cell, batteries. We had sort of radio transmission components, and the electric pump, of course. What we haven't tested is the coring device and then packaging everything in an underwater drone. And you think drones might be super advanced. In reality, what we need, which is just going, maybe 5-10 meters underwater, is technology that's been there for 50 years. So now the most advanced drones go down to 3,000 meters plus to survey the ocean floor, and they do all sorts of robotic things, picking up objects, fixing cables, taking samples. We don't need to do any of that. I mean, the most complicated thing is exactly taking one thermal device up up and down when you finish pumping, and the rest is relatively simple. So we think it's doable and it is scalable. So actually we went through a lot of the calculations which we want to run with you as well going forward. So we see this ecosystem, if you want, where there is a global operation system which will get access to a lot of data. Imagine your satellite observations on a daily basis, ice extent, thickness, snow thickness, whatever you can get access to that can help you with the dynamic planning. And I'll explain in a bit why we need to be so dynamic. Then we'll position the equipment at the beginning of the winter, including providing the necessary energy. The hubs will control a bunch of drones. The drones will re-ice an area, and then once we are done, it's a mobile solution. We can actually shift to the next area and continue to work. Why all this? Why do we need the mobility? To reduce costs, because if you think about static infrastructure, obviously you need a huge amount of infrastructure to cover, you know, the millions of square kilometers in the Arctic. Plus, you need to be mobile because you don't know where the work is needed most. There's no point in re-icing an area if you still have perennial ice and it's very thick, and there's no point in re-icing an area that has no ice at the beginning of winter because it's not forming yet. So you need to be in the right place at the right time. And this, we are talking about weeks to take decisions based possibly on past patterns. This is a bit of calculation. We don't need to go there. We talked about the importance of reflectivity. It's just simple calculation of the albedo effect for the whole of 2023. If you see there's two lines, which are the sea ice area and extent. The extent is where we have at least 15% concentration of ice in any given area. And the green curve is basically the energy that is reflected back to space on a daily basis. So this is the daily total. If you see, we get in the middle of the summer to more than 16,000 terawatt hours, which is more than 50% of the energy produced by humanity in a whole year. So there's a lot of energy being reflected back. This is purely on simplistic assumptions, if you want, on cloud cover, albedo, etc., but relatively accurate, let's say, in the scale. So why do we need a dynamic solution? So think about, again, this is 2023 sea ice concentration, where you see the white is more than 90%, where you see the purple, it starts to be lower, down to 15% or so. So the first bigger picture is the summer minimum, so mid-September, roughly 4 million square kilometers. That's where we get, we had a minimum in 2012, even much lower, but that's where we got over the last few years. So only at that point, basically, we know where it's most effective to intervene, because we know which ice is going to need, let's say, thickening to possibly survive longer in the following season. So there's multiple different approaches. One is to go where we still have perennial ice and try to thicken it up so it can last a few more years for the whole year. Another one is go where the ice has disappeared, maybe for a month or two only. And as soon as it starts to grow again, and you see the following quadrants as it, within a couple of months, it fills up the Arctic again. You can go to the new ice, and if you thicken up the new ice, then you give it a chance to become fullier again, and maybe to become again perennial ice. It's based on many other factors which will have to be predicted, so we need quite an intelligent solution. One is, where is that ice going to be next year? Because actually, the ice moves around. There are currents, depending on where they are. They might stay, the ice might stay in the Arctic for 4 or 5 years, or just go away the following year, potentially. So there's a lot of intelligence that needs to be brought into the system. So this is the sort of full-scale deployment, the logic, how we would move the engineering from side to side every few weeks, or be prepared in any given region with a sort of potential hypothesis of where it's most effective. In reality, we need a system that needs to be scaled to that side. We start from the small scale. So our idea is that in the small scale, this is the best place to start. And this is where we were, Cambridge Bay, Victoria Island. Why? Because at the beginning, while we learn with the new engineering, we need to be close to existing settlements for logistical reasons, and we need to be in areas where potentially we perform other important services. One is a service of ecosystem preservation and restoration. If you're thinking, this is an area where there is, Inuit population, and there is, obviously, we are interested in the wildlife going around those areas, which includes land and sea mammals and many other species. So we know how important the sea ice is in that ecosystem, and this is an area where the ice is now disappearing for at least 2-3 months a year. By adding weeks or months of ice in there, we might actually help the wildlife and the ecosystem to survive, which is fast disappearing, and possibly give some good service to the local population, to which depend on sea ice to hunt, fish, and to move, crucial for transportation. So we would start from an area where it's relatively easier, and then as we learn, then move, if you want, start to operate in areas which are increasingly more complex, until the point where you can afford to say, we can approach the current perennial ice and try to strengthen it, so we maintain at least that amount of full year ice. So that's the sort of general, if you want, planning ideas. We went through some calculations. You find the numbers in the recording, high level, but this is to give you an idea now, because how many of these underwater devices will you need? So a single drone with these specifications, so just 1.5 kilowatt as a pump, so this is less than your toaster if you want, can actually re-ice 2 square kilometers per season in these multiple cycles that we were talking about. So there will be daily cycles, weekly cycles, etc. So this is based on an assumption of how much thickness of ice we add, which is also based on the amount of snow that we find on average. So we are putting here 20 centimeters of snow thickness on average, and we are assuming this will add 0.5 meter of extra thickness to the ice at the end, which is conservative. The paper we were talking about earlier was talking about flooding the snow for 20 to get 70 centimeters extra. This is a University of Washington paper from 2021. We're thinking about 50. So how much energy would we need to operate the drones and that pump to re-ice 2 square kilometers? 4.6 megawatt hours. Again, it sounds like a lot, but 2 square kilometers is a big area. And if we look at the energy that we reflect in that area, it's massive. So it's not a lot of energy. I mean, the efficiency is a massive number. We are thinking about a pilot where if we get the right answers over the next 2-3 years in terms of does it really work, do we expect it to work, etc. So we would get to a pilot of maybe 100 square kilometers where we try to also give answers about any potential side effects, impacts on wildlife, nature, environment. Are we creating anything that we would not want to do, possibly incorporated in the method or the engineering? And thinking about the full scale, if we were able to cover 1 million square kilometers a year, we think we would be able to preserve the ice that we currently have, roughly 4 million square kilometers at the end of the summer, and possibly grow it back to where it was in the 80s. We would need 500,000 of these relatively small scale drones, and we would create, this is another important metric, goes back to the spiral of the first page, more than 500 cubic kilometers of new ice every year. And consider that at the end of the summer, we have about 5,000 cubic kilometers left in that spiral. And every year we grow naturally about 15 to 18,000 cubic kilometers. So 500 plus 500 is a big chunk, which in theory again contributes to the preservation of that ecosystem. So this is where we are with the calculations that we would be happy to validate and go through your checks. And finally, money, because it's always about money to make these projects. We went through an exercise of costing the operations, which includes everything, the people that operate it, the energy, ships, hubs, platforms, the drones themselves, how much would it cost over a number of years to scale to the maximum. We are talking about, when we reach full scale, about $6 billion a year. Again, big number, but we think relatively small given the size of the problem that it's trying to resolve, and 43 billion over a 10-year period while we do incremental scaling. So that's where we are with our calculations, again, to be validated and discussed more in detail, but we think we are on a reasonable, let's say, footing of feasibility, if you want. If the method works, we don't have any significant impact. We think this is something to be tested going forward. That's basically it.
Great.
Wonderful talk, Andrea. Thank you so much. You've really put us in the picture very firmly. What I first of all want to know is, are you observing saline water, high salinity water running off? And secondly, I noticed that the ice has a higher saline content than the ice that is there already.
Yeah.
And therefore I'm questioning whether that has a negative impact.
All good questions. I think with our sort of single experiment, we can't answer the last question, but hopefully with the lab tests we will. So what we observe is that the high salinity water that we pump on top of the existing ice, first of all, it freezes fairly quickly. I mean, a layer of 20-25 centimeters was frozen within 2 days, between 1 and 2 days. So after day 1 was still a bit slushy, and then on the second day when we went back was totally solid frozen. And then after a few days, that salinity migrated on that new stack from the top to the bottom. I'm not sure about the runoff of salty water. Sure.
The content,
yeah,
surely means the ice is colder than 0 degrees centigrade. Otherwise, it wouldn't be ice.
Yeah, the ice was at the top was at -30, -40.
Right.
So
Right.
obviously with the temperature, with the atmospheric temperature is what you also observe on the top of the ice. Then once we pump the water, the temperature increases quite significantly because of the warmer water, but still remains frozen, and it helps freeze the new layer. But I'm not sure about the salty water runoff observation. No.
So it's a really important question, Dave, though, because it might be fine in the depth of winter.
Yeah.
But the bigger question is, it might not be quite so fine when it gets to May, and therefore does the ice start melting sooner than it would otherwise have done as a result of the brine?
Yes, high salt.
Yeah, exactly. And therefore, what's going on right now is that the snow flooding from the measurements they took was just start, and the local people are now taking measurements of ice thickness. Is it on a weekly basis?
Yeah, it's actually it's been concluded because we froze through the full stack to the bottom of the ocean there, so nearly 3 meters. It wasn't deep enough.
You've gone to the ocean floor.
We've gone to the ocean floor, but the control area still has a ½ meter of liquid water.
Right. So this is really important, but ultimately there need to be experiments because but the local people are the ones that are doing the measurements in the
So can I just follow up that question and ask about the wonderful costing you're setting out there, which frankly looks like a big number, but it's peanuts. And I just want to say this because it isn't only the people in the Arctic region that are impacted by this. It's the whole goddamn planet. We're talking about Greenland, as you showed very beautifully there. Greenland, when we go back up to 9.5 square kilometers, when we go back up to full scale of ice, Greenland north coast gets covered in sea ice, and that protects the melting ice on Greenland. It's that big loss in the summer that is resulting in what looks like irreversible loss of ice from Greenland. And that loss is amounting to 50 tons an hour at the moment, right through the year over 10 years. We're talking about a vast amount entering the oceans, potentially pushing sea levels up 7.5 meters. And of course, we've got all the other challenges from the warming Arctic to the whole planet. We're experiencing this at the moment. I think not too many people are talking about 2023, but we've got all the data in now. In 2023, the ocean levels of the world are now suddenly rising in temperature. Not a tenth of a degree compared with 2022, but 0.2, 0.3 degree. So what we're seeing, I think, is all a consequence. I don't know if you've read Wally Brooker's book published back in 2009, the great American climate scientist. And he said, what happens in the Arctic and the Antarctic will determine what happens around the planet. And this is why the computational exercises are in great difficulty, because they don't include this.
Yeah.
So we have a false lead from the Intergovernmental Panel on Climate Change, which doesn't acknowledge what's already happening. So all I'm saying is, this is peanuts compared with the problems we're up against. Who, though, is going to come up with the money? Are we going to get governments to understand this? And then what is that procedure?
Yeah. So we see this possibly starting, let's say, for the initial scaling, being supported by some scheme like biocredits, and there are countries like Canada which have already started to fund, and it's really ecosystem preservation. How much does it cost to preserve, the biology, the biosystem, the biosphere? But going forward, hopefully this will be a global fund, maybe managed by some United Nations agency and contributed by all the countries. Because when you recognize that it's a global problem, it should be just costed and paid into a fund, as opposed to every country, every state having its own little thing. But
I've just got one more point to add, and I think it's quite important because in that political process that you've just mentioned, and it will involve governments funding it, whatever technique is used. We need to get the United Nations on board. Now, I'm in close contact with the Secretary General. He agrees with us, but he's got 197 nations to take with him. And, his hands are tied when he's talking in public. He tries to say as much as he can. There's a real challenge there.
I think one thing to point out is you go back to the very first graph. That the light blue line is the lowest emission scenario from the IPCC, and that's still over 2/3 chance of there being an ice-free Arctic, and that's the lowest
in 2040.
Yeah, 2040.
Now we also know we don't have to have an ice-free Arctic for all of these challenges to roll through. It's already happening. 50 million tons of ice an hour.
Yeah, I mean they chose million square meters as a but it's a threshold, it's nominal.
Any other questions? Any questions? Won't take you first.
That's a very important question, and we're actually talking to the people who might help us with the engineering to make it as friendly as possible with wildlife in two ways. One, you don't want the wildlife to be curious and try to interact with that. And the other way, you don't want to create noise, vibration, so the wildlife is disturbed. It must be taken into account into the engineering and the planning. Definitely part of that. And also obvious, but the pollution and anything else happening to this should be minimal or not. That's the idea.
I mean, it is a rich question because, you know, on ecosystems, there might be some bits of the ecosystems that are supported, right? So polar bears and things like this, and yet there might be other parts of the ecosystem that are impeded. So the answer might not be very clear. It might be rather messy.
We are heading for a total collapse of that ecosystem. But so not doing anything is our base, is the control. Sort of.
I think the answer is messy.
If you're going to argue that, oh, well, these mammals are going to get disrupted, but look at all of the other things. So, yes.
The impact seems pretty large, but the energy usage seems pretty insignificant compared to global energy use.
Yeah.
So why is there so much attention to zero carbon energy?
Zero carbon because we don't want to pollute the Arctic. It's still a pristine region. We don't want to bring, diesel generators and stuff that makes everything black, which would be negative for other reasons, or spill oil into the ocean. When you have an automated solution, you need to make sure that there's really as little as possible impact on the environment. So this is why hydrogen is a good way to store energy, transport it to the devices, transform it back into power, producing no emissions. It's not a combustion engine, it's an electric pump, so there's really water in and out of the system.
There is also an argument about just acceptability. And so your point is extremely well taken, but on the global scale, it's a drop in the ocean, excuse the bad pun. But we do need the support of the local constituents and everybody like that. So there's more to it than just the raw numbers. Herbert.
You talked, excuse me, you talked about flow down the slope. Now I did, it was hundreds of years ago, the problem of flow down an incline, and after a while it grows instabilities, and that of course changes the situation. Now I said to Shaun some time ago, a calculation done the flow down the cone. To seem to good geometry, and I've done some experiments in Australia which seem to validate that. It would be interesting to get together and
yeah, definitely. I didn't observe any instability in my experiments, but possibly because I always had a continuous flow of water over the whole surface, so didn't perhaps take it for a long enough distance that instability.
Well, definitely the length scale will depend on the flux that you put in, on the angle. Yeah,
that's why I think Jacob looked at the channel flow, a 1D and a radial, as helping at least provide some balance, because an instability could be an amalgam of, I guess, linear figures, right? But it's just at the moment trying to be, I guess, simpler by looking at 1D and just 2D. Well, to get bounds on the overall.
of course, a simpler version of what you just said is using dimensional analysis. You can get the result. More, quite close, and the constant will only be pi squared on 10 different.
Question, yeah.
I'm interested to hear about the consultations you've had with the local community, and in particular, what were their thoughts regarding geoengineering more broadly? Because obviously it's something that's very big and large scale and wanting to do lots of good things, but it's also a different approach.
So the people we spoke with were not really too concerned about geoengineering in general. They're really thinking about what they are observing, the changes they're observing, which are very dramatic. Permafrost melting, then losing their houses. They cannot travel on the ice because it's unstable. The elders cannot predict when it's good to go out for hunting anymore, which is dramatic for them. And they, there's a part of them, I guess, which is about, it's happening. What can you do? Just let it go. Like demoralized if you want. But there's a part which is very supporting. I mean, a big part was like, you're the first ones to come with a message of hope, because typically people have gone and measured, predicted, and said it looks bad and done that. So I think in general, they appreciated the message of intervention if it does help. They will always ask, what's in it for me? Because we are coming from far away and trying to do something which in theory is good for them, but in practice they want to be convinced.
And also just to follow up on that, if trying to think about using Inuit local knowledge in this, do you think there's scope to consider like taking information from them as to where you're going to put drones and where areas priority seasonally?
This is we could have spent another half an hour there. They are the experts of the ice. They know exactly how it forms, when it should form, how solid, in which areas it will stay longer or not, currents, animals. They are the experts. And they, in our view, eventually they should be the ones running this. It wouldn't make sense for other people to go in and run it like you run, I don't know, an oil well or something else. They should be owning it and running it because they're the experts and they own that land. So,
and talking of the biodiversity, they were talking about how certain areas the ice is disappearing faster, and so the caribou are migrating later or earlier or in different places. And so that's where somewhere where if you were going to go for a more local, ecosystem or benefits for them approach, they're the ones who tell you, okay, this is where the caribou normally migrate, this is where the ice is disappearing. And perhaps it's only, relatively small scale compared to the Arctic, but for them it's a huge impact. But they're the ones who provide that knowledge of this is where
it's a huge impact. Don't get away.
Yeah, but in terms of the area you're covering, perhaps it's a relatively small area in terms of extent, but the impact for the caribou or the impact of their travel routes is enormous.
Yes.
And just a quick question, Jacob, I'm certainly no expert, but it's, you're looking at heat loss via conduction, heat transfer via conduction, but are you also looking at the heat loss by evaporation, a strong Arctic gale?
So for these experiments, we considered those, so that in those experiments they were much smaller than the conduction and the advection, but it's longer term, bigger experiments, and definitely. So I think my next experiments in the boxes, I'll be looking at evaporation and convection because those experiments are going to run for a lot longer, and so they will be considered when they're of the magnitude where they make a difference.
Which sort of led me to think then, is there then also potentially another scope for effectively snow cannon powered by undersea water?
So the snow cannon, the issue is power requirements shoot up massively. So it's one potential thing you do. Also, if you're producing snow is not the same as making ice. But at the same time, one consideration is, okay, what if you think about, okay, we've made more ice at the start of the winter, that's thickened out, we're going into the summer. If you add snow on top, the snow is insulating and therefore slows down melting. So you might want to eliminate the snow at the start of winter, get an increase in thickness because you've got no snow, and then put snow on top at the end of winter when you come into the summer. And that would be the biggest benefit of a snow cannon type of ice.
We expect part of that to happen naturally, because at the end of the winter there will be more precipitation, but it's absolutely the idea to top it up with more snow if you can. You have probably very similar engineering, you just need a slightly different pump in terms of head and power, but it could be the same mechanism to produce snow at the end of winter.
And when it's atomized, that would be huge.
Yeah.
Any other questions? Good. Well, I really want to thank Andrea and Jacob. They did most of the talking, so thank you ever so much indeed for a wonderful, wonderful talk, and we wish you the very best. Thank you.